this is all the stuff that we've learned, actually. A lot of stuff. And I'm happy to go over anything you want to go over and review. So where would you like to start?
Can we go over R or S configuration?
Sure.
That stuff, 'cause
Yeah, so do you want to do like from the practice?
Yeah, sure.
Let me see what I got here. Oops, no, that's where I was. Okay, so like these I have on here. We might have seen some of these before. So is there anything particular about it that you have difficulty with?
I just feel like it's been a while since we've gone over
Yep.
so I can't really remember.
Right. So the key about this is really looking for the priority, which has priority, and making sure you're good about that. So selecting the priority rules for each of the groups are most important. Then, of course, which way that lowest priority group is pointing. Most often that is going to be, let me just do this here. Most often that is going to be a hydrogen. So, for example, that hydrogen there, if we're looking at this carbon in yellow as the stereogenic carbon, right? And then we have priority groups. So from that carbon, you have a nitrogen, hydrogen, so that's, and a carbon and carbon, right? And so it should be pretty easy to see that's number 1 and that's number 4. Then this one versus that one, which would have the higher priority? Yep. Yes, so this would be 1, oops, wrong pen. 1, 2, and 3. The one attached to sulfur, because then sulfur has the higher atomic number. So that would get precedent. So then what's the configuration for that molecule? Remember, clockwise, with the lowest priority group pointing away, clockwise would be R, counterclockwise would be S. So hopefully that one's pretty easy to see. That should be the R configuration. And then, of course, remember the thumb thing? So pointing the thumb back into the board, it would be your right hand versus your left hand. Okay, this one, I think this one confuses people a little bit. This carbon here. Okay. Let's see. So that'll be 1, 2, 3, 4. Hydrogen again is the lowest. So we have sulfur, nitrogen, or carbon. Hopefully that's not too difficult. That would be 1, 2, and 3. And again, it's going clockwise, so that's also R. Okay, how about that one? That carbon right there. Priority group. So what do we have? We have a carbon, and a nitrogen, and a hydrogen. So we know, again, hydrogen is the lowest. That'll be 4. Nitrogen versus carbons. So nitrogen is going to be 1. And now we have a carbon and a carbon, right? Carbon and carbon. So which has higher priority?
The carbon bonded to the oxygens.
So you have carbon bonded to oxygens, right? So this would have 3 bonds to oxygen, right? That carbon would have a double bond oxygen and then a single bond oxygen. This carbon is attached to 2 carbons and a sulfur. Yeah, see? Yes, so that's somewhat a little bit tricky, so be really careful in looking at that. It's the carbon attached to the sulfur. No matter how many bonds there are to oxygen, the sulfur gets the atomic weight priority. So that would be number 2 and 3. So that would be going clockwise, but the lowest priority group here is coming out of the board. So which hand do you need? Yeah, your left hand, with the thumb pointing straight up. Would be S. Exactly. Let's see here. Yeah, this one's pretty good too. That stereogenic carbon is a good one. We have an oxygen and then 3 carbons. So the highest priority is going to be the oxygen, right? And then we have to take a look at the 3 carbons. That carbon, that carbon, and that carbon. So which is the lowest priority?
Probably the one on the top right, because there's nothing else connected to it.
That's right, it's just attached to 4 hydrogens. So notice that's a carbon, the yellow one is a carbon that's not attached to any hydrogens, right? It's easy to spot a hydrogen as the lowest. If there are no hydrogens on it, you have to look a little more carefully to see which is the lowest. So carbon with 3 hydrogens, this is a carbon with 1 hydrogen and then 2 other carbon bonds. And this is a carbon with 3 bonds to carbon. And so the bond with 3 bonds to carbon would have the highest priority over the one to 2 bonds to carbon, over the one to no other bonds to carbon. Okay, so 1, 2, 3 would be R or S? S, yes. Okay, notice this carbon does not have any hydrogens shown, but there is a hydrogen on there, and it's pointing in which direction?
Maybe towards us.
Yep, it'll be pointing towards us, so like I can draw it in to remind myself of that. So we have nitrogen, carbon, carbon, hydrogen, 1 and 4, and then we have a carbon and a carbon. So it would be the carbon attached to oxygen would have the next priority, and then 3 would be that one. Okay, so that would be also the S configuration.
So why is nitrogen higher than oxygen? Oh, 'cause
It's not.
directly.
It's carbon. Yeah, so it's nitrogen versus, yeah, careful about that. Nitrogen versus carbon.
Okay.
Yeah, so only one layer on. Go layer by layer. And now we have 2 carbons, and it's the carbon attached to oxygen over the carbon attached to carbons. Okay. Any other stereogenic carbons in this molecule?
One of the OHs.
Yeah, so let me erase this a little bit here. It would be this carbon right there. Okay, that's an interesting one. So we have carbon. Yeah, interesting. Okay, carbon attached to oxygen, and then 3 carbons. This is going to be number 1 here, this oxygen. But now we have to think about that carbon versus that carbon versus that carbon. What would be the highest priority? Yeah, the double bonded oxygen, this would be second. The one that has 1 bond to oxygen and 2 bonds to carbon would be third, and then this one that's attached to just hydrogens and carbons would be 4. Okay, so this is a little tricky to see. What's the configuration of this one? What do you think? Which way do you have to point your thumb if you're going to use your hand? Now this is a tricky because the lowest priority group is in the plane of the board. It's not coming out or going back, so you have to look at it really carefully. And so, and then you have to, this one is going to the back, right? Number 1 is to the back. So if you're going from 1 to 2 to 3, you're going this way, right? So if you're going to look at it, you could look at it from the bottom, but if you stick your thumb straight up towards that group, you need your left hand to curve this way. One in the back to 2. If you try your right hand, it goes from 2 to 1. See that? Okay. It's a little bit more difficult to see when you have them in the plane of the board. So this would be the S configuration. Does that help? You need to see more?
No, that's it, thank you.
Okay, let's take a look at this one actually, just identifying the types of carbons. I'm asking a lot of things about this molecule. So looking for primary carbons in this molecule. Just want to make sure, yes, how many primary carbons are present in this molecule? What's a primary carbon? What do you think is a primary carbon? Attached to one other carbon, yeah. And I don't think I really explained this well when we were talking about the substitution. We usually are referring to primary, secondary, tertiary, and quaternary on sp3 carbons. So for example, this is a carbon attached to only one other carbon, but it's sp2 hybridized. We don't use this nomenclature for or identify it as that because it's not tetrahedral. So we're usually talking about tetrahedral sp3 carbons. So the number of primary carbons, so where would they be in this molecule? Here's one. Obviously anything that's a methyl group on the end is going to be a primary carbon, so those yellow ones. Any others in here?
With one that's double bonded to the oxygen and then also bonded to the nitrogen.
No, those are sp2. Any of the sp2 hybridized carbons we don't consider here. So we don't even use primary, secondary, tertiary for those carbons. Okay, but there is one other primary carbon in here. You see it? The one that's bonded to the oxygen, yes. So that carbon, yeah, so if this were ethanol, let's say that's an OH, this were ethanol, we'd call that a primary alcohol because it's an alcohol attached to a primary carbon. In a larger molecule like this, it's easy to spot the methyl groups, but be careful of things attached to non-carbons. So I just wanted to make sure, point that out, just to make sure you're clear. And again, I don't think we explained it very well about that primary, secondary, tertiary carbons. We're talking about sp3 hybridized. We don't use it for those. Okay. Any other questions? Let me just go through this. Okay, aromaticity. Remember aromaticity? Which of those molecules are aromatic? What do we need to have aromaticity? 3 requirements. Remember what they are? Yes, you have to have a contiguous pi bonds on every carbon or every atom. It has to be a p orbital on every atom, so you need conjugated pi bonds. You need to have it in a ring, and then you have to have one more criteria. Yep. 4n plus 2 number of hydrogens. Number of electrons. 4n plus 2 number of electrons. So which of these meet this criteria?
Well, the first one's.
First one and the second one, yes.
And the third one.
And the third one.
The last one.
And the last one. Yes, not this one because there's sp3 hybridized carbons that interrupt the conjugation. For these two, right, we have a lone pair of nitrogen involved in the aromatic ring or not? No, there's already a double bond on the nitrogen. So remember, if it's already sp2 or that double bond is already to the atom, the lone pair can't be in the same plane as the ring, whereas this one has only single bonds to it in the ring, so the lone pair is orthogonal to that. So it's in the ring electrons. Good. Yeah.
Sorry, why is the last one?
Because we have a benzene ring in there, so it's an aromatic compound. Even if there's another substituent on it, there's a benzene ring. So there's an aromatic component in there. Okay, any questions on acidity? I think it's pretty basic. Yeah, for example, this question, I've given you the pKa, so hopefully it wouldn't be too difficult to answer something like that.
What is, I kind of forgot because this was a while ago.
Mm-hmm.
Do you favor the more acidic or the least acidic?
Which is more reactive? If it's more acidic, would it be more reactive?
More
And if it's more reactive, is it more or less stable?
less.
Right, and so any reaction would favor going towards
Oh,
more stable, less reactive, less acidic.
Okay, so you could,
So the equilibrium, this equilibrium, right, so here we have, first of all, acid and base, because it's the one that has the proton that's being given up, and the base is what accepts the proton. And then on the other side of the reaction, we would call the conjugates. So the acid on the left, the conjugate acid on the right would be what had taken the proton, what ends up with the proton. And the conjugate base would be what's left after the proton's been given up. Okay? In the reaction that's written in this direction, right? But now we have pKa of 4.76 on the left and 0.23 on the right. So which is the stronger acid?
the one on the right.
The one on the right, exactly, stronger. So the reaction would favor equilibrium towards
The left.
the left side, the more stable side, lower energy. Exactly. So could you rationalize that without being given the pKa numbers? Would you be able to figure this out without the pKa numbers?
Well, the right side has, what's it called, fluorine in it,
Mhm.
which would probably mean it's a stronger acid. So then you would just assume that the left is lower.
That's right, yeah. So about acidity, obviously given the pKa numbers, it's pretty easy. You can just say, well, the lowest pKa is the more reactive, so we'll go for the more stable side of the equation. But if you didn't have the pKa numbers, I wouldn't expect you to know if their molecules are really close to each other, but if there's stark, clear differences in structure, that would give you an idea about which would be more acidic. Those are what I'm looking for. More electronegative groups is the base and conjugate base, which is the more stable anion, that would be the more stable side of the reaction. If that's delocalization, right? Fluorines are helping to stabilize the negative charge through inductive. If there's differences in resonance, the one with more resonance structures would be more stable. So that means the negative charge would be more stable. Its acid relatively would be more acidic than the other acid. See how those are all connected? Good. Good. All right. Okay. Substitution, electrophilic halogenation. So here we're using chlorine in the presence of iron trichloride. That's a Lewis acid to make Cl+, right? So we have Cl+ as the electrophilic species in this that's going to react with phenol. I've shown two of the three possibilities. One is the meta attack, and one is the para. So we have the meta product here and the para product of those two pathways. So in this example, I haven't drawn in any of the remaining double bonds and charges. So this problem would ask you to fill in the missing things in this mechanism. So where would you start with? So if I'm attacking this carbon, that's where the chlorine is, the metacarbon, how would I draw that in arrows? Well, the electrons here are reacting with the chlorine to form a bond to the chlorine. That means the double bond is broken. So it's this double bond from the original structure that we've changed. The other two double bonds are still present, so I would draw those in. Now what happens then with those electrons? Where are they in this structure? Those two electrons are where in this structure?
Are they on the carbon that the Cl is on?
Well, they're still attached to that carbon, but they're in between the carbon and the chlorine. So those two electrons are what's making the bond to the chlorine. Okay. So just to recognize that those two electrons became that bond, and so what's left then on this carbon?
Plus charge.
A plus charge, exactly. Right, because the electrons left that carbon. Okay, so then we can draw resonance structures for this, right? In this case, we can move those two electrons over one position, and that takes the electrons away from that carbon. The other double bond remains the same. So the plus charge and the double bond swap, and so the plus charge moves from 1 to 3. The double bond moves over. And we can do that again, putting the plus charge there, the double bond there, and the double bond there. And so those would be the 3 resonance forms for the meta position of the attack of the chlorine plus. Right? Okay, so what's different here? In this case, we've reacted with the same double bond, and so the chlorine is now in the para position. The double bond that was there remains, the double bond that was there remains, and then this is the carbon with the plus charge. And you can draw resonance forms like that. You can draw a resonance form like that. And what I didn't ask to be drawn here, but hopefully you recognize, there's a 4th resonance form I could draw from this, right? From which of these 3? What's the 4th resonance form? Yeah, the middle ones, because there's lone pairs on the oxygen, which can form a double bond to the carbon with the plus. I should have drawn some more room here, which would look like that, where the plus charge then it gets extended even further out to the oxygen. So the oxygen in this case is stabilizing that plus charge. So that particular resonance form is particularly more stabilized. This overall intermediate with all these resonance forms is more stable than the one on top, where the oxygen can't directly participate because the oxygen in the top never is, the plus charge never ends up on the carbon that the oxygen is attached to. So there's no, the oxygen itself can't directly form a double bond to the plus charge. So the bottom would be more stable, intermediate, and so that would be the major product for electrophilic aromatic substitutions. That's one example. Chlorines, Cl+, right? What are the other things we can do with electrophilic substitution? So if we wanted to put on an NO2 group, oops, where'd my thing go? If we wanted to put on an NO2 group, what are the reagents we use? The reaction conditions?
Oh, like what do you do?
So if we wanted to, see here we used chlorine, Cl2, and FeCl3 to put on a Cl+, right? If we wanted to put on an NO2+, what do we need to use?
H3O and L2.
Close. Yeah, nitric acid in sulfuric acid. So if you recognize that, that combination, that's an NO2+. If you have SO3 and H2SO4, what is the electrophile that generates? So what kind of group would we put on the ring if we use those reagents? Not OH minus. It comes from SO3, but it's actually, the electrophile would be HSO3 plus. So that would make a sulfonic acid. So sorry, I don't have a lot of room to write here. So that would put on, for example, you'd put on a benzene ring, you'd end up with a sulfonic acid group attached to sulfur. So for instance, HSO3 plus would have an S plus. That's what reacts with the benzene ring. Sulfonic acid. What else could we add on? We could add on a carbon group. So any carbon group like methyl, ethyl, etc. We can use aluminum trichloride with some carbon group like methyl chloride. You can put on a methyl group. We can do acylation, so anything that has a double bond oxygen, acid chloride, which we learned about just this past week, right? Acid chlorides with AlCl3 makes this group plus and puts on an acyl group. So remember all those different types of things we can add to a benzene ring. Is there anything else we could add? Bromine, Br2 and FeBr3, or I think that was all, right? What can we do with groups once they're on there? Is there anything we can do to modify groups that are on the benzene ring? There were a couple of reactions, right? So we can take things with alkyl groups, as long as there's at least one hydrogen or oxygen bond on the carbon next to the benzene ring. KMNO4 makes what? Remember that? What would that make? So remember that this will oxidize groups next to the benzene ring and convert it into a carboxylic acid. So that was one thing we can do to modify groups. Remember, we don't have a way to put on a carboxylic acid directly onto the benzene ring using electrophilic substitution, but we can take a methyl group and oxidize it. Let's see, anything else about aromatic chemistry? You have questions about? We'll come back for more. Oh yeah, this is an important aspect of aromatic chemistry. I forgot to mention this. The type of group that's on there affects the next reaction and so on, and so you need to know how it affects it. But of these groups, we have groups that make the reaction with benzene rings faster than the unsubstituted benzene itself, and some groups that make it slower. So we activators or deactivators, right? And so those are, if it helps to make the reaction faster, what kind of group is it? Donating, right? Electron donating. And so that would be directly like resonance donating when you have lone pairs directly next to the benzene ring. That's an electron donating group. Alkyl groups are electron donating groups. So those will be electron donors. Electron withdrawing groups. Nitro group is a strong electron withdrawing group. Anything with a double bond to like oxygens or something is an electron withdrawing group. An electron withdrawing group, okay? So the electron deficient or electron withdrawing groups make the reaction slower than benzene. They deactivate. So what did I ask? Which would react faster than benzene? Would be the ones with electron donating groups. If that group's on there, another reaction with the benzene would be faster than if you didn't have the group on there, but it's just benzene itself. Also affects the position, right? So donating groups direct the next incoming group where? You're right, ortho and para, if it's an electron donating group. And if it's an electron withdrawing group, it would direct it to the meta position. So those are meta directors. So those ones. Yes?
What makes the CH3 a donating group?
CH3 is a donating group. It's weaker than a direct resonance one, but it's a weak donating group. If you think about its ability to stabilize a carbocation, right? Remember, carbocations are more stable if you have more alkyl groups attached to it. So primary, secondary, tertiary carbocations, the tertiary would be more stable. And that's because of the electron donating ability of just an alkyl group. It's weaker than resonance, but it's still helping to stabilize plus charge. Good question. All right, we haven't really done a lot of naming problems, but you should hopefully recognize and be able to pick out names. So are you able to assign the right name with these? There's obviously more names than there are molecules here. So what kinds of things do you look for in a name? This is a whole mix of different types of molecules and functional groups we've had throughout the semester, from alkenes to halides to green compounds, carboxylic acid derivatives. So for this first one, we have a carboxylic acid, and so we're looking for something that has acid in the name. And there would be a couple of these here. This one and this one. So which one would be the correct name for that molecule? Yeah, E. 4-nitro benzoic acid. So benzoic acid takes the name of that's the parent benzoic acid in a nitro group in the 4 position. Another way we could call this para-nitro benzoic acid. You could use the number, or you could use the para when you have di-substituted benzenes. Okay, how about this one? What's the parent? It's a derivative of carboxylic acid, and it is what kind of compound? And not an amine, it's an amide. If there's a CO double bond, it's an amide. An amine wouldn't have the CO double bond. So this is an amide, and then we need to figure out how many carbon chain it is. So 1, 2, 3 is the longest chain. So it's a propanamide. It's from propane. I have one. Here's a propanamide. Here's a propanamide. Which one's correct? B, that's right. 2,2-dimethyl propanamide. So this would be B. If it were J, what would the structure look like? Well, how would it be different?
Methyl groups would be attached to the nitrogen.
Exactly. Those would not be on there. It'd just be a single chain, and we'd have 2 methyl groups on the nitrogen. That would be J. Cyclopentane, right? Cyclopentane, so this would be 1,3 substituted. This is a bromine and a methyl group. And that would be, let's see what's up there. There's A and D. And it's just the difference in those two, 1 bromo, 3 methyl, cyclopentane. The difference is just the stereochemistry. So, yeah. What would the stereochemistry be?
1s, 3s?
1s, 3s would be correct, yeah. So that would be A. See that okay? Yeah. Hydrogen's coming up on the bromine. 1, 2, 3, 4, 5 carbon chain. So it's a pentenol. Alcohol would be the functional group. 1, 2, 3. So it starts on the 3 to 4, and it is which stereochemistry of the double bond? Trans, yeah. So it would be trans 3-pentene 1-ol, or pent 3-ene 1-ol. As long as you know which number is associated with which functional group. I think nowadays IUPAC would say pent 3-ene 1-ol. I learned it this way. Alkyne. Which one would it be? Let's see. This one would be, here's an alkyne. Here's an alkyne. YNE ending. One would have a 1, well, this should be pretty easy to see just from the position of the alkyne, 1-ine versus 3-ine. So this is not attached to an N carbon at all, so it can't be a 1-propyne or 1-ine. It should be the 3. So 1, 2, 3, 2-chloro 3, 2-chloropent 3-ine. So it should be this one, and hopefully it is the R configuration. Yes. All right, that one. Name it. Start number from where? Yep. The double bond gets precedent here. So it's a pentadiene, so it's a 1,3-pentadiene or a pent 1,3-diene. With a methyl group on the 4 position. And there is no cis or trans here because there's no double bond that can have different isomers. That's because those 2 groups are identical. Okay. Okay, any questions on naming? Okay, here's some reactions. Oh boy, okay. I'm just looking and I don't see how to do number A. I wonder if I have the right thing here. Oh no, it's there. Okay, never mind. So what's happening in A? What's going on in this process?
We're adding a methyl group to one end of the triple bond.
Yes, notice we're adding an additional carbon. Okay, why isn't that working? We're adding a carbon there. And to add a carbon onto an alkyne, we first have to do what to it? There's a hydrogen there now. Remember what we can do with alkynes that we can't do with other carbon-hydrogen bonds? We can actually deprotonate it and make a C-, make the alkyne into a nucleophile. And we use a base NaH, or sorry, I think we use sodium amide, right? NaNH2. NaNH2 takes the proton off the end of the hydrogen, and then we can add a methyl halide. And so that would be somewhere here. It would be C. NaNH2 followed by iodomethane. That'll extend that carbon chain. B? B should be easy. Alkene, and we have a chlorine. We've added HCl across the double bond, so that should be easy. That's F. Ketone, and we have added this group on here and broken the double bond to the oxygen, and we end up then with an OH. So ketone, we make a tertiary alcohol with the addition of a benzene ring. So we need what kind of reacting group for the benzene ring?
An acid?
Not an acid. We need the equivalent of a benzene minus, right? And so we need a nucleophile. So what do we know that is a carbon minus? This would be A. So this is the Grignard reagent. Phenyl magnesium bromide would be a benzene ring with a magnesium bromide, and that's made directly from bromobenzene by treating it with magnesium metal. Remember the Grignard reagent? All right, so in this reaction, what's happening in this case? We have a double bond. We are doing a reduction. So we're adding hydrogen to the double bond. And we do that with hydrogen gas and a metal catalyst, palladium typically. Is that what I have? Yes, hydrogen with palladium on carbon. Hydrogenation of a double bond. That would be H here. Phenol, if you treat it with a reagent, you can end up putting bromine on there, and if you have enough of the reagent, you can add 3 of them on there. And notice they are in the positions that are ortho and para to the OH group. So we need electrophilic bromine, a source of Br+, and that would be, which one? This one. Bromine with iron tribromide.
What would happen if we added just HBr?
If you add HBr to phenol, what do you think would happen if I did that?
Substitute them.
No.
We just add a methyl group next to it.
No. Nothing would happen. Nothing would happen. HBr, well, there may be some kind of equilibrium between protonating the OH and deprotonating the OH, but bromine minus isn't going to do anything with the ring. We need strong plus. If you add an H to the ring, if you add a strong H plus to the ring anywhere, the only thing that can happen is H plus comes off. So pretty much nothing would happen. You'd really need, to get bromine on, you need a form of Br plus. And that would be the bromine with the iron tribromide Lewis acid catalyst. Yeah, HBr will react with regular double bonds. Like if you add HBr to this, you'd get bromine and H, just like we did with HCl, but not with a benzene ring. Carboxylic acid, and we're putting on a sulfonic acid group. So for that, we need to have,
H2SO4 and an SO3.
yes, so that would be here, and I called it fuming. Fuming sulfuric acid just means it has SO3 in it. Yeah, so notice here, concentrated H2SO4 wouldn't do that because there's no source for the SO3. We need to have SO3 present with sulfuric acid. Good. Okay, any problems recognizing functional groups?
What would E be?
What would E be?
Yeah.
E. So it's a CO double bond with a hydrogen and a carbon. So carbonyl compounds, but it's not at the oxidation state of carboxylic acids. It's the aldehydes and ketones. So here's a CO double bond with 2 carbons. So one of those is an aldehyde and one's a ketone. Which is which?
E is an aldehyde, A is a ketone.
That's correct. Aldehyde and ketone. And C would be an acetal. B, carbon-nitrogen double bond, that's an imine. And A, not a super stable molecule, but we have a carbon with 2 bonds to oxygen, so it's the same oxidation state as an aldehyde or ketone, but to 2 OHs, that would be the addition of water to the ketone, so that's a hydrate of the ketone. Different than an acetal, so we have OCH3s, or OR, some kind of carbon. Doesn't have to be CH3. That's an acetal, that's a hydrate, ketone, imine, aldehyde. And if I had OCH3 and OH, what would that be?
A heavy acid.
A hemiacetal, right. Hemiacetal, halfway to the acetal. Or, yes. Good. Any other derivatives of this? I don't think so. Okay, what else did I put on here? Go. Okay, these are carboxylic acid derivatives. Right, so this shouldn't be too difficult. COCl is an acid chloride, right? C double bond O, CN, that's what? An amide. Okay, so we have a CO double bond, O, and then another CO double bond. Anhydride, right. 2 acids where we've lost water would be an anhydride. So that's 2 CO double bonds with an oxygen in between. CO2H, there happens to be 2 of them on there. That hopefully you recognize as an acid. And then this one, ester, right. C double bond OR, O carbon, that would be ester. Mm-hmm. I like this question. So here are alcohols, products, and there's various starting materials or mixtures of starting materials. So a Grignard reagent and a carbonyl compound. And so to make that alcohol, one of those is the mixture that you would need to make that one, or make that one, or make that one, or make that one. So, what do you think?
Did you use D for the first one?
So D for the first one, so we have benzene ring and a hydrogen, and we're adding a benzene ring. So if we mix that together, we would get, the question is, where does that methyl group come from? Yeah. So here we have phenyl. There's a hydrogen unwritten there, right? There's a hydrogen unwritten there. There are 2 hydrogens here, and no hydrogens on the last one. So that's a clue. So, so of the carbon that's attached to the oxygen, that carbon bond to either phenyl or methyl had to have been made, and the other group had to have been on there already. So the Grignard reagent here would be, it wouldn't be A, that has a phenyl and a methyl, but then we would add another phenyl, so that would end up with 3 carbon groups. We need something with a hydrogen. So which one is the only one that could come together, have a phenyl, methyl, and hydrogen? F, exactly. There's the CH3, there's the hydrogen, and we're adding the phenyl group, so that would be F. I know, they all look very similar, right? Because the way, lots of pHs and CH3s. Look at them carefully. So A, the first one has to be F. The second one, 2 phenols and a hydrogen. Which one brings together a molecule with that would end up with 2 phenols and a hydrogen?
It would be D.
D, correct. D. There's a phenyl group and a hydrogen on there already. So phenyl and hydrogen would be on there already, and then we're adding the next phenyl group. Yeah, you recognize that now? Hopefully that helps a little. The next one, methyl, we have a CH3, a hydrogen, and a hydrogen on there. And when we're using a Grignard reagent, we're adding a carbon, and so the only thing you need to look for is, this is the Grignard reagent we have to add, CH3 magnesium bromide, and then we have to have a CO double bond that has 2 hydrogens on it. So it would be G. CO double bond with 2 hydrogens, and we're adding the methyl group. And the last one has 2 phenyl groups and a methyl group. So one of those, either a benzene, a phenyl magnesium bromide, or CH3 magnesium bromide needs to be added. So if we were to use, so H would have a phenyl magnesium bromide, but two carbon CH3 groups. So we don't have that. We have 2 pH groups. So that would be, that would end up with 3 phenyl groups. It would be A, right? Has to be A is the only one that would give that product. Another way to think about this, yeah, there's more options than there are questions, right? And so one thing you could also look at is just draw the product of those and see what they would be and then match it. If it shows up in that list, it would be right. If it doesn't, it wouldn't. But recognizing how these alcohols are made, again, if you're looking at how you would make an alcohol using a Grignard reaction, you're looking at all 3 things attached. And something with a carbon is something you're adding with a Grignard reagent. And so if you're going to add a phenyl group as the Grignard reagent, as the nucleophile, that means you have to have a CO double bond that has a hydrogen and a phenyl on it already. Okay, good. Good, good. One of my favorite questions. What are the relationships? In this case, we're looking at mostly conformation and stereoisomers of various kinds. First one would be diastereomer, yes. Nothing, no bonds have changed. The atoms are all attached. That double bond is even in the same place. The only difference is the stereochemistry of CH3 on the left and the right. The bromine stays the same. So in this case, one stereoisomer stays the same. One is the inversion. So it can't be a mirror image. So it must be a diastereomer. B?
Identical.
Those would be identical, yes. All I've done is lifted the left molecule up off the paper, flipped it over 180 degrees and put it back down. And if you want to double check yourself, you can look at the positions, like the bromines. What is the RS configuration? Is it different or the same? And the same thing for the CH3s. C? What's different in C?
Just where they're placed.
What are
Like,
placed?
The oxygen, the double bond on oxygen
Mm-hmm.
is like originally there, but it's in the ring.
Double bond has changed. What else has changed?
The position of the hydrogen.
The position of the hydrogen, right. So we actually have atoms moving to different places. So everything else being the same number and kind of atoms?
Constitution.
Yes. Good. And if I draw a chair structure, I'm usually going to be talking about a conformation. So this is the chair structure versus the boat structure. They're flipping back and forth at room temperature typically very fast, but if I were to draw frozen conformers, those would be different conformers. And the last one.
Identical.
Nope. They're not identical. What's different?
The thing, not the thing, but whatever it's called at the end, like how the left, it goes up and on the right it goes down. But I don't know what it's called.
Well, the chain, so let's look at this. This is 1, 2, 3, 4, 5, right? And this is 1, 2, 3, 4, 5. Notice the fluorines have just been moved over a little. If I were to take this molecule and turn it and flip it, it would have the 2 fluorines down. So think about this. So in the 2 position, what is the configuration of the stereoisomer? What's the configuration of that stereoisomer? And that one.
S and
Mm,
R and S, I should say.
this one is R and this one is R. 1, 2, 3. Okay. So 1, 2, 3 clockwise, hydrogen's down. 1, 2, 3 clockwise, hydrogen's down. So you see that okay? Okay. What is the configuration of the one on the right?
S and then R.
Oh, wait a minute. Sorry, maybe I'm mistaken. Ah, that's right. You were right. These are identical. 1, 2, 3. That would be R and R. Sorry, I thought I had the chain the same way. If I were to put it here up, it would be S and S, right? See, even I have to look at this carefully. That's why checking this configuration, if I had drawn it like this would be the enantiomer. Then this would be S and S. That's what I meant. That's what I thought I was looking at. But it's not.
I have a question about B.
Yep.
Why isn't that considered an enantiomer?
Maybe I did mix these up. Did I mix this up? This is going to be R, and hydrogen is coming up. So that's R also. So this is, oh, sorry. Yeah, that's R, clockwise, hydrogen down, right hand, right? And this is bromine. With the hydrogen up, you need your right hand.
Okay.
So R and R, and this is 1, 2, 3, that's S and S. So looking carefully at the configuration. So what, were you seeing something else there?
No.
Okay. Good. Okay, this is a question about understanding stability in a number of different contexts. We have some conformations, we have some stereochemistry, we have some chemical features, so some resonance effects. And so there's lots of things that affect relative stabilities of things that we've talked about throughout the semester. Acid chloride versus amide. The difference is it's a different derivative of a carboxylic acid, which is more stable. Acid chloride or amide? Amide, yeah. And we talked about the differences in those carboxylic acid derivatives, and it has to do with the bond strengths, the enthalpies of the bonds. Chlorine is more reactive because it's a better, weaker bond, better leaving group. Cis versus trans double bond. Trans, yeah, and that's because of the crowdedness of the cis configuration. Axial versus equatorial groups on a cyclohexane. Equatorial is more stable, right? Less crowded in the equatorial positions. For steric reasons. 2 carbocations.
Or substituted.
More substituted versus less substituted. Yeah, so primary versus tertiary. That's one thing. There's another aspect of stability here. Yeah, resonance. The one on the right can actually delocalize because it's next to that double bond, and so you could spread that plus charge out. And the one on the left you can't. So this one would, for both of those reasons, would be the most stable one. Configurations. These 2 conformers of bond rotation of butane. The left one will be more stable, right? The 180 degrees anti-configuration versus the gauche. Good. I think that's all I had on this problem set. Did you see the synthesis problem I put up in the problems, in the in-class problems section? What I have here is starting from benzene, doing all of these reactions, what is the final product? Okay, these are all reactions we've seen this semester. So, who can do this? Let's take a look at the first reaction. What's happening in this first reaction?
Are we adding a methyl group to the benzene ring?
Yep, we're adding a methyl group to the benzene ring. So we can just draw the benzene ring. I'm just gonna write a circle, it's easier. With a methyl group on it. So we make toluene from benzene, methyl benzene. Okay, I posted a key, by the way. This was put into the in-class problems as sort of an extra at the bottom. Okay, if we react that with potassium permanganate,
Do we get the something carbox? I don't know what it is, but it's like the double bond of oxygen and the OH.
yes, it's a carboxylic acid. We make benzoic acid. I can draw it out there, or I could write CO2H. Benzoic acid we make by oxidation of the methyl group to the acid. Okay, we take benzoic acid and we react it with thionyl chloride, SOCl2.
We take out the OH and add in chlorine.
Take out the OH and add a chlorine, yes. So we add a chlorine. So you take an acid, carboxylic acid, and it makes an acid chloride. SOCl2 also reacts with alkyl alcohols, right, to substitute OH and replace it with a chlorine. Okay, so we made an acid chloride. And we take that acid chloride and react it with this molecule, this amine, in the presence of pyridine. Remember, pyridine is there just to neutralize HCl that's generated in the reaction. So it's this is the amine that's reacting. And so what happens when you take an acid chloride with an amine? Yeah, it substitutes the chlorine. So it adds to the CO double bond, and then the double bond reforms and the chlorine leaves, and we end up with, so that nitrogen, and the hydrogen comes off, that's the part of the HCl. So that nitrogen forms a bond to the carbonyl where the chlorine was. The rest of the ring that the nitrogen is in is just attached there. Doesn't have to be a ring nitrogen, but in this case it is. Okay, so we have an amide. So notice this is all chemistry we've talked about recently. Acid to make an acid chloride, react it with an amine to make an amide. Now we have this molecule, and we want to react it with nitric acid and sulfuric acid. Yes.
Are we going to add NO2 to the pair position?
So that's a good question. Yes, this is a way to generate NO2 plus, so that's what's being added to the benzene ring. And which position would it go to? It would be meta, yes, and why? Because we didn't specifically talk about amides necessarily, but notice this benzene ring. This is an electron withdrawing group. It's a CO double bond, just like if it was a CO2H, if it was an ester, an amide, that CO group is an electron withdrawing group. If you were to put a plus charge on the carbon next to it, that would be bad because the resonance forms for that CO group would have the electrons going towards the oxygen, right? So you're putting plus next to plus. So it would be a meta director. And I'm just going to draw this, let's see, on the bottom here. Let me draw it on the bottom. So this group is here, nothing happens with this. And we'll put nitro group there in the 3 carbons away from the CO double bond. Okay, now we're going to react that. We have this molecule with a chlorine, carbon chlorine, sp3 carbon chlorine, and aluminum trichloride. And that's going to put on what kind of group? This makes that plus charge. And so that's the group that adds, the 3 carbon group is going to add to the benzene ring. And what position will that go? Well, if this is a meta director, that's going to direct to that position. This is a meta director, that's going to direct to that position. So we're going to put the alkyl, the carbon group on that position. Are you following this okay? Remember all this? So then we will have, let's see if I can draw this on here. The benzene ring, the amide is just sitting there, nothing happens to it. The nitro group is there, and then we have a 3 carbon group attached with a double bond on the end. So notice I've drawn it 1, 2, 3 carbons with a new bond here. Okay. React this with HBr.
Does the double bond at the end of that little arm there get replaced?
Replaced with,
Bromine?
well, it doesn't get replaced with bromine.
Do we instead have a bond with bromine?
Yes, H and Br add. So H plus adds to give the more stable carbocation, and then bromine adds to the carbon next to that. And so the product would be, let's see if I can draw this again. Bromine there. The rest of this stuff still stays. So notice what we did. Of that 3 carbon group, proton added, Markovnikov addition of HBr, proton added to the least substituted carbon, bromine adds to the more substituted carbon. Okay? Way back in the alkenes, addition to alkenes chapter. Okay, this is sodium tertiary butoxide. And this kind of reagent is what kind of reagent? We usually use this as a base. Kind of a bulky base. So we don't get O- adding or anything. It's reacting as a base. So we have an alkyl halide. Remember the alkyl halides chapter? In a strong basic conditions, we do.
The bromine and the sodium come together and we.
Yep, and then that is taking off a proton, right? We're doing an elimination. So we reform a double bond. So we do an E2 elimination. Form a double bond, but where's the double bond at? Let me draw all this on. NO2 is there, our amide is still there. And then that 3 carbons, where's the double bond?
It's all like carbon 2 to 3.
Yeah. So notice that process. So we do this reaction to put on this 3 carbon group. The double bond is on the end of that 3 carbon chain. In order to move that double bond in, we can add HBr across that, because that'll selectively put the bromine on the more substituted carbon. And then we can do an elimination, which gives selectivity for forming the more substituted double bond. And so in this way, we've migrated the double bond over a position from the left molecule to the one all the way on the right. Okay, now we can take water with a sulfuric acid catalyst and acid catalyst. Acid catalyzed hydration of alkenes. Remember that? So we're adding OH to the double bond, right? And where does the OH add to? Amide is still there. Nitro group is still there. The double bond, you add proton and OH across the double bond, hydration of the double bond. And will the OH be here or will it be here? Which is the more stable carbocation? This one, right? If you add the H plus here and have the carbocation here, that carbocation then is delocalized with resonance in the benzene ring. If you add the H plus to this position, the carbocation is here, it's just a secondary carbocation. So it's a more stabilized carbocation in that position, and then that's where water adds. So we do acid catalyzed hydration to put the OH in that position. Then, finally, sodium hydride reacts with an OH group to do what?
Peel off water.
Doesn't peel off water. This is taking the proton off to make a minus charge on oxygen. So this, remember, we make an alkoxide. So you can deprotonate the alcohol with sodium hydride. And that alkoxide can react to do SN2 chemistry. In this case, we have a carbon with a bromine on it, which we can do a substitution reaction with. So it's an SN2 substitution. So this is a way to make an ether. Remember our alcohols chapter. React alcohols with sodium hydride. It is basically, it's just deprotonating the OH completely because it forms H2 gas. So we can push that reaction all the way to completion. Make O-, react it with alkyl halides to make an oxygen carbon bond. We can make an ether. And the final product would look like, I probably don't have enough room to draw it. Let's see. Benzene ring here, nitro group down there, amide over here. That stays all the same. We have 3 carbon group, we have oxygen, and then we have attached to a CH2, and then attached to another benzene ring. So that's the final product. So what is that, about half of the reactions we've talked about in class? Maybe. Any questions on any of these reactions here? I did post this key in the in-class problems folder, so it's there on the bottom.